Today's topic is hydride reductions of nitrogen compounds. We're going to cover three mechanisms that involve reducing an amide, nitrile, and imine. The reduction of amides and nitriles involve lithium aluminum hydride, followed by an aqueous workup like we've seen before. And the reduction of imines involves a new reagent called sodium cyanoborohydride, and that works a lot similar to sodium borohydride. A ketone or aldehyde can be reduced to an amine using sodium cyanoborohydride and a nitrogen nucleophile. Sodium cyanoborohydride is used rather than sodium borohydride since sodium borohydride would simply reduce the ketone, and the cyano group makes it more selective. For the ketone to turn into the primary, secondary, or tertiary amine, it needs to go through the imine intermediate. So before we cover reductive amination, we're going to go over how an imine is formed, which we've covered in class. We start with the ketone, which is protonated. The nitrogen attacks the carbon, and water comes in, takes the hydrogen off the nitrogen, forming the tetrahedral intermediate. In order to create a leaving group, the alcohol group is protonated. It leaves and creates the resonance-stabilized carbocation and major resonance structure, which is the double bond between the carbon and the nitrogen. Water comes in, deprotonates the nitrogen, and it forms the final imine structure and an acid byproduct. This is the partial mechanism for the reduction of an imine to a amine. Sodium cyanoborohydride will first, the bond between the hydrogen and the boron will attack the carbon. The electrons will be pushed up to the nitrogen, and the nitrogen will attack the boron. From there, the intermediate will be, the boron will dissociate from the nitrogen through an aqueous workup, and forming a product and the boron byproduct, which will associate with the nitrogen and any lone pairs within the solution.
An amide can be formed by acylation of an acid chloride using a primary, secondary, or tertiary amine. An amide is then reduced to an amine using LAH reduction.
So an amide is a resonance-stabilized structure. If we push this bond onto the oxygen, we get a negatively charged oxygen and a carbocation. A hydrogen bond from LAH will come and bind to this attack and bind to the carbocation, and the negatively charged oxygen will bind to the aluminum, resulting in the structure where hydrogen is bound to this carbon and oxygen is bound to the aluminum. Then electrons from nitrogen are pushed to this bond, and resulting in the oxygen-aluminum complex to be coming off of the structure. This creates a double-bonded C double bond N, and the N to be positively charged. But if we do resonance structure and move this bond to the N, this causes the N to be neutralized and a carbocation to appear. Thus, a aluminum hydrogen bond can come and attach here to the carbocation, and the N can come and bind to the aluminum too. Then after aqueous workup, we get our final product.
A nitrile is formed when a halide or tosylate is attacked by a cyanide ion. Then the nitrile can be converted to a primary amine by reduction with lithium aluminum hydride.
So a nitrile is formed, but nitrile is resonance stabilized. So by pushing one of the bonds from the CN, we get a resonance structure where the nitrogen is negatively charged and there's a carbocation. Thus, a hydrogen bond from the LAH will come and bind to the carbon, and the nitrogen will attack and bind to the aluminum. Then this creates a structure where the aluminum is bound to the nitrogen and the carbon is attached to one hydrogen. So the hydrogen bond from the aluminum, it attacks the carbon again, and one of the bonds from the CN pushes one of the bonds from the CN to go onto the nitrogen. This creates a structure where carbon is bound to two hydrogens now, and nitrogen is still attached to the aluminum. Then, after aqueous workup, we get a structure where carbon is attached to two hydrogens, and nitrogen is protonated with the aluminum coming off and dissociating, and we get the amine.